first topic is a really quick review of gas laws. So on your study guide, Dr. E wants you to know what is STP, and I very specifically remember this being a test question on exam 3. I think she was asking like, what is STP? And the choices were like something, 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 something. So as long as you remember that standard temperature is 0 degrees Celsius and standard pressure is 1 atm, you should be fine for this topic. And then as like a bonus kind of information, at STP, 1 mole of any gas will have a volume of 22.4 liters. So as long as you know that this is 0 degrees Celsius and 1 atm, you're good. And then also recognize, or also be comfortable with converting Celsius to kelvins, because she might ask you like, or she might put the temperature in kelvins, and if you don't know that 273 kelvins is the same as 0 degrees Celsius, you might get it wrong. So know how to convert between those two. So the next topic for gas laws is going to be the average velocity of gases equation. And you should memorize this equation because there could be a problem on it. And the equation is, here's this.
I have slides, that's awkward.
Okay, the equation is velocity is equal to, or the average velocity of a gas is equal to 3 times RT all over the molecular weight of the gas. And then for this, it's really important that you know which units to use because the R is not the 0.082 whatever that you're used to. It's going to actually be the 8.314 joules per Kelvin times mole. And the molecular weight will be in kilograms per moles. So that I can cancel out with the joules. And then T is going to be in degrees Kelvin. Okay, so make sure that you pay attention to this, kilograms, and this. It's going to be a different R value. Okay. Okay, so the next topic on the exam is going to be diffusion and effusion. And for this, you just want to know what is the difference between the two. Diffusion is when a gas fills up a space. So if someone sprays like some perfume or something, the rate of diffusion is going to be how fast will that perfume spread throughout the whole room. And then effusion is when a gas leaves a space. So if you have like a helium balloon and you popped it, how fast will the helium balloon, or if there's like a hole in the balloon, how fast will the gas exit from the balloon? Okay, so now let's try a practice problem. You have a balloon filled with oxygen gas and carbon dioxide gas. Circle what the best choice is. So which gas has the highest average velocity? Is it oxygen, CO2, or are they both the same?
They are, well, they're both in the same balloon, but so they should have the same temperature between the two, but the difference is the molecular weight of them.
Yes, exactly. So let's rewrite our average velocity equation in case, so we can like look at it and, whoops, it's R, yeah. RT. Okay, so yeah, Michael is right. Because these two gases are in the same balloon, we can assume that they're going to be at the same temperature, right? So we can cross out temperature. That's not going to matter. The only thing we need to focus on is the molecular weight. So which gas has the heavier molecular weight?
It would be the CO2.
Yeah, it's going to be CO2. So remember in lecture, the example that Dr. E used, she was like, no offense, but typically if you're like fatter, you're going to be a little slower at running versus like someone who's skinnier, they're going to be faster at running. So this is like a good way, like it's kind of mean, but it's a good way to remember these gases and their velocities. Because velocities is basically like what speed are you going at? Like how fast are you moving? And because CO2 has the heavier molecular weight than oxygen, oxygen will be faster because it has the lower molecular weight, so it can move faster.
Oh, can I, never mind, continue, please. I was gonna, never mind. Okay, that makes sense. Yeah.
Okay.
Sorry.
Which gas will effuse out of the balloon the fastest?
Diffuse the fastest. It would be the gas that is the effusion is defined that the likability that for a particle to go through a small hole.
Yes.
So if we take into consideration the molecular weight of it, the one that has the smaller molecular weight should be the smaller particle. Mm-hmm. So that one would be the one that would diffuse the fastest. Over here.
Take over.
All right. So give me one different minutes. So that's a party. Moving on. Sorry, question. Hold your okay. Sorry. Let me finish this up right quick. So the one with the smallest. For any of y'all, you can ask questions in the chat box. We'll get to them once we have like time in the video. So ask away in the chat box. Maybe someone can actually answer it for you, for all of you. But yeah, so the particle with the smallest molecular weight would be the one to diffuse the fastest. Basically, it's kind of like I said, diffusion is where whatchamacallit, the likability that a particle can go through a small hole. So let me try drawing it out here. Draw. There we go. So like, let's say that you have a gas. Like, let's say there's two different gases, right? And then there's a small hole right here. I can draw it on here. Is it not drawing? Okay, that's okay. Time out. That was not supposed to be seen. Okay. Here. Sorry. Yeah, they're like blowing up the chat box right now. But we'll get to your questions like once we have. Oh, there's the chat.
Okay, so back to this. The gas that will effuse the fastest out of the balloon is basically the gas that is lighter, and because oxygen has a lower molecular weight, will look like this if you were to draw it. And then so if you had like a balloon and you drew a hole in it, oxygen will be able to move out. Last one, gas with the lowest average kinetic energy. If you remember, kinetic energy is only determined by which aspect? It's going to be dependent on temperature. Because kinetic energy is defined, or the definition of kinetic is basically movement, right?
Mm-hmm.
So if you measure the average, there is less energy in your system. So when the gas particles have less energy, they're not going to be moving around very much. They're going to be very slow, slower than normal. But if you suddenly added energy to the system by raising the temperature, they're going to be...
Oh, they can't hear me when I'm typing. Oh, my bad.
I think I'm too far away from the mic.
Yeah, let's just do it like this. Okay, so that means that, all right, so apologies for that. Great, we're going with this. This is like really awkward.
So yeah, basically, because these balloons or these gases are in the same balloon, they'll be at the same temperature, meaning the same amount of energy is going to be in the system for all gas molecules. So that means that this will be both the same kinetic energy or average kinetic energy.
To review back the fusion. Back to the fusion. So a fusion is the likability that a particle can go through the hole. So look at the right cylinder. See like how the difference between the big green dots and the little blue dots. The little blue dots have the more likability to get through the hole because like it has like a lighter molecular weight and with the lighter molecular weight, it'll end up moving faster. Does that make sense with everyone? Plus or minus here and there? The average kinetic energy part. So average,
Yeah, so average kinetic energy is basically how much is a gas moving. And this is only dependent on the temperature. It does not matter how large it is, does not matter how much of it you have. The temperature is what is determining how fast these or how much are these gas molecules in motion. So because these two gases are in the same balloon, we can assume that they're at the same temperature. So therefore, the gas with the lowest average kinetic energy will be none of them because they're at the same temperature. So they're both the same average kinetic energy.
Mm-hmm.
So pretend like oxygen gas was in a different balloon, and pretend CO2 was in a different balloon. And pretend CO2 is at like 100 degrees and O2 is only at 0 degrees. The gas with the more kinetic energy will be CO2. Even if CO2 is like larger and it's heavier and it's gonna move more slowly than O2, the average kinetic energy, which is like how much are these gas molecules moving, will still be CO2 because the temperature is higher. So hopefully that makes a little more sense.
Yeah.
Okay.
So
next one, this is going to use the diffusion and effusion equation. So if you remember what that one is, this is another equation that you should memorize. It's going to be rate 1 over rate 2 is equal to the square root of the molecular weight 1 over molecular weight 2. And then to make your lives easier, Dr. E says always put the heavy one on top and then the lighter one on the bottom. Okay, so I'm going to clear this so I have space to work. So a sealed container is full of hydrogen gas and methane gas. You poke a hole in the container, letting the gas out. Which gas will effuse out of the container the fastest and how many times faster? So for sure, which gas will effuse out of the container faster?
Methane. Oh, sorry. You said is the faster? Hydrogen will diffuse faster.
Yeah, so for sure, hydrogen will go faster, right? Its molecular weight is literally 1 gram per mole. So it's going to be very small and it's going to escape very quickly.
2 grams. It's hydrogen gas.
Oh, yeah, you're right. So again, here's the equation that we need to use to solve. Rate 1 over rate 2 equals the square root molecular weight 1 over molecular weight 2. To make your lives easier, always put the heavy on top and the lighter one on the bottom. So now let's try it. So we know for sure hydrogen is going to be faster. So this is H2 gas. Molecular weight of H2 gas is 2 grams per mole because there's 2 hydrogen atoms. Methane gas, 16 grams per mole. So which molecular weight should we put on top?
The heavier one, so methane.
So we're going to put methanes on top. So it's going to be 16 grams per mole over hydrogen gases molecular weight, 2 grams per mole. So we do the math. 16 divided by 2 is that. Square root of 8 is
square root 2 square root 3 square root 2.
It's going to be 2.828 so to answer the second part, how many times faster? Basically, hydrogen gas will escape from the container at a rate that is 2.28 times faster than the methane gas will. Okay, so this is your final answer. Yeah, sig figs. It's multiple choice exam. Just pick the closest one.
It's there, so
yeah. Okay. I love this static. Alrighty, density and molecular weight of gases equation. Another equation that you should memorize. She will not give you any equations on your exam. She will give you constants, but no equations. And there's a lot of equations to memorize, so please memorize this one. If you memorize this one, it should be easy because from what I remember on the exam, there was a lot of like plug and chug equations. So as long as you know the units and the equation itself, you should be fine and get some like easy points, you know. Okay, so please memorize this one.
density.
So let's see. Alrighty, density is equal to, where is it?
Right here.
Okay, wait, no.
Time out. This one.
Yeah.
No, it's this one.
Oh yeah. So density is equal to the pressure of a gas times its molecular weight all over RT. And then density is always in grams per ml. Pressure is in ATM. Molecular weight, grams per mole. R is the gas constant. It's like 0.082 something.
They said 0.6.
0.6. I forget the units.
Latin camel. So liters.
Oh yes.
Yeah. So liters times atmosphere divided by K times mole.
Yeah. And then when Dr. E gives you the constants, she'll also give you the units of the constants. So you don't have to memorize the units portion or the number portion of any of the constants. And then temperature is always in kelvins. Okay, so please memorize this equation. Guarantee you she will ask you a question about it. I know because I took the exam like 3 years ago and I still remember what was on it because I kind of tripped up and I think I forgot it. And yeah, so don't be like me. Don't like panic on the exam because you cannot memorize something. Memorize it now so that on Monday, it'll be really easy for you to just plug and chug. All right, let's try a practice problem. A gas has a density of 2.11 grams per ml at 95 degrees Celsius and 725 millimeters of mercury. So what is its molecular weight and what is its average kinetic velocity? So let's try it. We need to know which equation to use, which is going to be one we just wrote.
The density one.
Yes, the density is equal to.
So rho is equal to what? Oh.
Molecular weight all over RT. Okay, so because we're solving for molecular weight, I'm gonna change this equation so that molecular weight will be isolated so that it'll be a lot easier to just plug and chug. But to do that, I'm gonna multiply by RT on both sides, and that'll leave me with P times molecular weight. And then to isolate molecular weight, I'm gonna divide by P. So the equation we're gonna use is molecular weight is equal to density times RT all over P. So I'm gonna clear that and rewrite it.
Y'all can still hear us, right?
MW equals, okay, good, oh my God.
Okay.
Is equal to density times RT all over P. Alrighty, so now let's plug in our variables and make sure the units are all correct because if they're not correct, you will get it wrong.
get some funky, weird answers and stuff.
All right, so density is going to be 2.11 grams per ml. We don't need to calculate, or we don't need to convert anything because they match. R is going to be our gas constant, so 0.802.
No, 0.8. Yes.
0.08.
206.
0.8206. Okay, and then temperature is going to be in degrees Kelvin, but this is not. So we're going to have to add 273 plus 95.
60.
So it's going to be 368 degrees Kelvin all over P, which is the pressure in ATM. This is not an ATM, right? So we need to convert really quickly. I cannot do these in my head, so I'm going to write out like everything. We have mmHg, Hg is on top, so mmHg is on the bottom to cancel. 760 is equal to 1 ATM. Units cancel out, we're left with ATM. So we're going to have to divide 725 by 760, and we get 0.9539 ATM. Alrighty.
I have a question.
Yeah.
Doesn't the R constant have units of liters? So wouldn't we need to convert the density into liters also?
You're right. Okay. Wait, that means.
Oh wait, this density is in grams per liter.
Yeah.
Oh shoot. Oh, then that means.
Oops. Okay. So yeah, Michael made a really good point. The units of the gas constants is Latin, liters ATM over K moles, and this is in mLs. If it's in mLs, it will not cancel out with the liters. So we gotta do something to density to convert it to liters. So let's convert to liters. I'm gonna erase.
You can erase the pressure one.
I'll erase this.
Okay.
So let's convert density to the correct units. We have 2.11 grams per ml, but we don't want ml, we want liters. So how do we do that?
Times it put 1,000 milliliters on top and then divide by 1 liter.
Yeah, so to cancel ml would need to go on top and then liters on the bottom because they will be able to cancel out with each other. And then we know 1 liter has 1,000 ml. So our density will actually be 2.11 times 1,000. It's going to be 2,110 grams per liter. So we're not going to use this number. We're going to use 2,110 grams per liter. Okay. Oh my God. Yeah, be careful with your units.
Units are important.
Very important, very, very important. All right, so now everything is in the correct units. And to double check, let's check our units of the gas constant. We have liters, cancel out with liters, check. We have ATM, cancels out with ATM, check. We have kelvins, cancel out with kelvins, check. So now all that's left is going to be, change colors, it's going to be moles and grams. And this matches because the units of molecular weight is always in grams per mole. Okay, so now let's plug and chug. I'm gonna put my calculator. So 2,110 times 0.08206 times 368 all over 0.9539. You get molecular weight.
Yeah, no, it should be right because it's like the density is like very, very
dense,
compact.
Yeah, it's like twice the density of water.
Yeah.
Okay, you should get a big ass number. 667.97 grams per mole. Sig figs, right? Two sig figs. So this is going to be
67,000.
6.7 times 10 to the power of 1, 2, 3, 4. 10 to the power of 4 grams per mole. Okay, this is your answer.
That's one heavy molecule.
That is a thick molecule.
Hella thick.
Thick with 4 C's. Okay. Clear. All right, now next, what is its average kinetic velocity? So let's write our equation. V equals square root of molecular weight times 3 RT. I'm guessing it's going to be super slow.
Yeah, it's super slow. Mine's fix for exam for the sake of time. Oh, they're answering for you. Yeah, they're answering for themselves.
Okay, so let's plug in our variables. We have 3 times R. Remember, this is going to be the 8.314 joules
per mole K.
Per mole K times temperature, which was 95 plus 273, 368 degrees Kelvin, all over the molecular weight in kilograms per mole. So we're going to take the number we calculated last time. It was 66797 grams over mole. So we want kilograms, right? So what's going to be on the bottom?
The grams.
Grams on the bottom and kg on top. So we know 1,000 grams is in 1 kg. Grams will cancel out. We'll be left with kg over moles. So we divide this number by 1,000. We should get, hold up, that's right.
66.
Can't do mental math.
Oh, well, okay. I'm sorry.
66.797 kilograms per mole. So we plug this number into here. And now all we got to do is punch it in the calculator. So I'm going to do 3 times 8.314 times 368 over 66.797. And hopefully you should get 11.722 liters per second.
It's actually pretty fast for a molecule. So we have, this feels weird. All right. Oh, your phone, but the camera's like right there. All right, so
why do you switch?
Yeah, because like you're over here now, and I was like over here on your side or something like that. But moving on. So intermolecular forces. So there's 5 main types that you have to know, but in reality, you only need to know like the first 4. So you need to know lemon dispersion, dipole-dipole, hydrogen bonding, and ion-ion. Ion-dipole, it is another intermolecular force, and it is stronger than ion-ion, but it's not considered part of the first 4. So I'm going to bore you all with words. If y'all stay afterwards, I can show you how it's meters per second for the velocity. There's like a little derivative for that, but I'll show you all in conversions. I'll show you all for it later. So the first one is lemon dispersion. Well, it's one. I'll show you all how it's meters per second later. So lemon dispersion. Ow, my body. So lemon dispersion. It's the weakest intermolecular force, meaning that all molecules will end up having it, aka it applies to most molecules. Non-polar molecules will be the only one that has intermolecular forces, such as this methane over here to the side of us. And all the charges cancel out because electrons are evenly distributed. So, like example, think of CO2, you know, that it has like carbon is in the middle. I don't think I can like write on this besides like moving this. Can I write on it? Like, hold on, type on. annotate finally. All right, so like example, like C. I see nothing wrong here. Okay, so I can't draw the C. That's awkward. And I lost the stylus. That's even more awkward. Okay, so the charges are all evenly distributed. They're all evenly distributed over all the molecule. This is awkward. Can I even annotate on this thing? Oh, finally, sorry. C, oh, that's the reason why. C, like CO2. So like CO2, we know that, sorry. We know that carbon would be in the middle. That's a C, that's an O, not a 6. Carbon will be in the middle, and then you will have your 2 oxygens on the side. So even though that this pink color sucks. Hold on a second, let me clear this. All right, let me try this again. So carbon dioxide, oh, that's much better. So you know that carbon will be in the middle, and then on the side, oh, that's the chat box, that's awkward. The on the side, you'll have the 2, you'll have your 2 oxygens. So we all know that oxygens will have at least 2 lone pairs on them, and we know that lone pairs indicate polarity. The thing about it is that since this oxygen, one of it's going in this direction, and then the other oxygen is going this direction, the only London dispersion, the only force that carbon dioxide can only have or interact with is London dispersion, since we know that CO2 is a non-polar molecule. So yeah, hopefully that makes sense. Next. All right, next one is dipole-dipole. So dipole-dipole molecules will still end up having London dispersion because we know it's the weakest, so that applies to most, if not all, the molecules. And this mainly applies to polar molecules. So, and this is where they have an unbalance in electronegativity. So back to the carbon dioxide sample, see how that oxygen will move to the, one oxygen will move to the left, the other oxygen will move to the right, which is the reason why that carbon dioxide itself is non-polar, because its overall polarity becomes 0. But if we look at water, we can see that there's like an even distribution in electronegativity. We know that oxygen is a very highly electronegative molecule, and hydrogens, and the 2 hydrogens on the bottom are a lot less electronegative. So then they end up pointing towards the oxygen's direction. So the overall polarity of it becomes polar, which is the reason why that water is such a very, very polar molecule, is because of that interaction. So yeah, the next one, please. All right, hydrogen bonding. So hydrogen bonding only applies for hydrogen. So that means that, so for hydrogen, it can only bond to 3 specific molecules: fluorine, oxygen, or nitrogen. So only those 3 with hydrogen can only make the hydrogen bond. But hydrogen bonding itself can also have a dipole-dipole moment and also a London dispersion, because London dispersion is always applicable to most, if not all, molecules. So like an example test question would be, Dr. E gives you a molecule. How many intermolecular forces would that molecule have? So example, let's say, oh, Claire, let's say that one molecule is H2O. Let's say H2O. So how many intermolecular forces can H2O have? 3. That is right. So, since H2O has London dispersion, we already know that's 1. Dipole-dipole, because we already stated before, it's a polar molecule. And then hydrogen is bonding with oxygen, which is one of the fun letters. So that's why that's why H2O can have up to 3 different intermolecular forces. Next, please. Thank you. And finally, the last one is ionic. So ion-ion. So how this works is that ion compounds they will form an ion-ion force, but they make it into like a lattice structure, which is like seen over here on the bottom right. So how it works is like the negatives. So this one here on the bottom right is salt, which is like the easiest to like explain for ion-ion. So how it works is that the positive, so it's like positive, negative. So the interaction between that positive, negative ions is this force itself. There is a London dispersion force between them, but since it's considered to be very, very, very like weak compared to ionic, it is completely ignored. But there could be a London dispersion force to exist, but it's like very instantaneous. Like, I don't know, it's like, there, that's it. That's the only force it has. But yeah. So, and then finally we'll cover up with ion dipole. So this happens when you add a soluble ionic compound into water, which is this is the best example that like explain it. So how it works is that the water will pull apart the ionic compound into its cation and anion, and the interaction between like the cation or anion and the partially negative or positive of the wasted of the water molecule is the ion dipole. So how it works is that whatchamacallit, so the highly negative portion of water will surround the positive ion, and then the highly positive portion of water will surround the negative ion. So it's like that whole opposites attract thing, which is the reason why that like when molecules are dumped into water, they can break them apart, which makes that ion dipole. So why is my hand covered in? Oh, this is a pen. That's awkward. Moving on. So force practice problem. All right. So I want to, I can't read on this. Okay, fine. All right. So for this practice problem, I want to know what is the from ranking them from from least intermolecular force to highest intermolecular force of H2, N2, H2O, NaNO3, and highest to least, yes, highest to least. So high to low, IMF. So from high to low, IMF. So H2, N2, H2, NaNO3, and I'll throw in HCl in here. HCl. So how will we order this from high to low? What do we have to look at first?
Lewis dots?
Yeah, we can look at, we'll look at the Lewis dots first. So for HCl, we know that it's a linear shape, but we know that Cl has lone pairs with it because it still has to complete the octet rule. Now then, is this polar or non-polar?
Polar.
Polar, because of the lone pairs that chlorine has. So these lone pairs, even though the structure is linear, the lone pairs, sorry, give it an overall polarity direction of, yeah, I know I sneezed really bad. Give an overall polarity in one direction. So thank you. So this is the reason why that HCl is very polar. So if we know that's polar, what can we say about its intermolecular force? We'll have we just jumped, lol. What do we can say about its intermolecular forces? Would it have an ion-ion?
No, because it's covalent.
Yeah, it's covalent. So we know it doesn't have an ion-ion because it's a covalent. 35 participants. Does it have ion dipole?
No.
No, because it's not in water.
It's not ionic.
Yeah, it's not
in water.
Yeah. Will it have hydrogen bonding?
I want to say yes, but it's no.
It's no. Yes, it doesn't have hydrogen bonding because it's not part of FON. And but does it have a dipole?
Yes.
Yes. Polar molecules. So polar molecules will have dipole. Yeah. Dipole. Yeah. So so again, if you have any questions, just post it in the chat. Maybe one of your classmates can actually answer it for you, and we can continue on with the session. So polar molecules will have a dipole. So we know that HCl will have a dipole. So let me just I'll make sure to mute all your cameras and your mics, please. Make sure to mute all of that, please. And if this can erase, this would be nice. It's not erasing. It's like it doesn't love me anymore or something like that. All right. So I'm gonna speed run this a little bit. So give me one moment, please. So HCl has a dip, and we all know that all these have LDF. So LDF for all of them. So this one, and technically speaking, this one, but it's ionic, so this is we'll just say that it has it. All these have ion. So this one's a dip. H2 will only have limb dispersion, right? Because it's
covalent.
It's covalent, yeah. So H2 is covalent, but
they share everything equally. They share electrons equally.
Yeah. So H2 and N2, they both share electrons equally. So they only have is LDF. Water, we stated before, has H2 has H bonding because it's part of FON. A dipole because it's polar, and then an LDF. And then finally NaNO3. Who's driving? Moving on. NaNO3. So whatchamacallit? So NaNO3, is this an ionic compound? Well,
yes.
Yeah. NaNO3 is an ionic compound.
Na plus. Yeah. And what is that again? Polyatomic ions?
It's a polyatomic ion, yeah. So it's
what is that again? Nitrate?
Nitrate, yeah. Na plus.
Right. Yeah.
And NO3.
This is a good review for the final.
Yeah, NO3 minus. So this is sodium nitrate. So sodium nitrate is a polyatomic ion, and it is soluble in water because all nitrates are soluble in water. So it has so it only has ionic. That's a bar. Why is there a bar? Get away, bar. So this is ionic. So now that we have all of that, I'm going to clear all the drawings. Actually, wait. Yes, great. So actually, how do I do this? Let's just erase it. So let's just erase this part. So if we're going to rank them, if we were going to rank them from high to low, what would be first? The one with the, it would be the one with the, whatchamacallit? It would be the one with sodium nitrate. It would be sodium nitrate would be the first one that we're like, would be the first one because it has the highest IMF, which is ionic. So sodium nitrate will be number one. It's an awkward color. Can you, what the hell, computer? What the actual hell are you doing there, computer? All right, sodium nitrate will be the first one. We know that H2O would be the second one because it has hydrogen bonding. HCl would be the third one because it had, between the last three options, it's dipole. Now then, to separate N2 and H2, you would have to look at its was molecular weight or electrons? Or N2 and H2 when they're tied.
N2. It's a number of electrons.
Number of electrons. So you look at the number of overall electrons. N2 will have more electrons than that of hydrogen. So that means nitrogen would be 4, and then hydrogen would be number 5. So that's the order. So from high to low, sodium nitrate, H2O, HCl, N2, and H2. All right, so on with the next one. Intermolecular forces and their effects on physical properties. So as the strength of intermolecular forces increases, these 5 will have a what you call a reaction to it. Well, not a reaction, change of behavior to it. So as viscosity increases, which is like the thickness or like the friction of it, so it's like hella thick or something like that. It's like hella thick. Excuse me. Why can't I tap this?
What are you drawing?
I know, but like I'm trying to. You should be able to tap on it like that. Maybe we're supposed to be tapping on it. But... Oh my gosh! Oh my gosh! Oh my gosh! Oh my gosh! It's great. We're going with it. All right, viscosity. So as the intermolecular force increases, viscosity also increases. One really Shaniqua looking video. I apologize. So as viscosity increases, the strength of the intermolecular force increases, viscosity increases. Surface tension. As surface tension increase, as intermolecular force increases, surface tension. Can you go back, computer? What the hell's wrong with you? Ah! This is awkward. Okay, there we go. Increases. So Grease says, so as surface tension increases, as strength of the intermolecular force increases, surface tension will also increase. So and boiling point will also be the same. So as the strength of the IMF increases, so does the boiling point. And the heat of vaporization also increases with the stronger intermolecular force. The reason behind that boiling point always increases is because of whatchamacallit, the strength of intermolecular force increases. The boiling point also increases. So have you tried, so like think about boiling water. You would have to put in like X amount of energy to boil the water in order to break that that hydrogen bond it has in the liquid phase in order to break it apart. So that's why you have to put in like temperature to increase, to get it to change its phase. That's the reason why that it takes like so much energy for you to boil water, because you're putting in like more and more until to actually break those bonds between them. That's what happens with intermolecular force. So with a stronger intermolecular force, the stronger it holds it together. The stronger it holds it together, which means you need more energy to break it apart, which is the boiling point. So then, vapor pressure, on the other hand, decreases with higher intermolecular force. So I can't think of an example right now.
Well, we got to think about the definition of vapor pressure, right?
Yeah.
What is vapor pressure?
The pressure of the vapor?
No. Vapor pressure is basically how likely are you to be a gas. So the higher your vapor pressure is, the more likely you will be a gas at any certain state. If you have a low vapor pressure, it means you are less likely to evaporate into a gas, for example. So rubbing alcohol versus water, when the doctor puts like rubbing alcohol on your skin, alcohol has a very high vapor pressure because once you put it on, it's gonna like go away after like 30 seconds. If you put water on your skin, it's gonna take a lot longer for the water to evaporate, which is why alcohol will have a higher vapor pressure than water. So in terms of strength of intermolecular forces, Think about an object with a very strong intermolecular force, like ionic compounds, for example, like NaCl. That's a salt, right?
Yeah.
If you put salt in a bowl, is it going to evaporate?
That would be some lit ass salt, though.
No, right? So that means salt has a very high strength intermolecular force, which is ion-ion. That's like one of the highest strength of intermolecular forces, right? So that means salt will have a very low vapor pressure because of that strong intermolecular force. It's not gonna be unstable and evaporate into the air. Unlike rubbing alcohol, if you just spray it on like your computer screen to clean the screen, it's gonna be gone after like 2 seconds because rubbing alcohol is a liquid. It's not gonna be an ion-ion intermolecular force. It's gonna be instead
dipole.
Yeah, it's dipole, which is like much weaker than ion forces, right? So that means alcohol will have a higher vapor pressure than NaCl because it has a much weaker intermolecular force. It's going to want to be a gas at any given state. Hopefully that makes sense.
Hopefully.
Now we're going to move on to thermodynamics. So for this, you need to know 2 terms, or actually 3, endothermic, exothermic, and specific heat. So endothermic is basically when energy is absorbed or added into the system, and exothermic is when energy is released or removed. And the definition of specific heat, you should know this actually. Yeah. So specific heat is what we use to calculate T change equations. And this is basically how much energy do you need to raise the temperature of 1 gram of a substance by 1 degree Celsius. And the important thing to remember about specific heat is that it is specific to different types of materials. So iron will change temperature more differently than water will. So it's going to have a different specific heat depending on the type of material you're using. And then one more is the heat of vaporization or heat of fusion or heat of whatever. I forget the word is called for that.
Which one?
Delta H.
Oh, enthalpy.
Oh yeah, so the change in enthalpy is basically how much energy do you need to change 1 gram of something into a gas or into a liquid.
Just a phase change in general.
Yeah, so that is for how much energy is required to do a phase change, but specific heat is how much energy do you need to do a temperature change. So make sure you know the difference between those two, because on your exam, Dr. E will give you these numbers and you'll have to memorize the equations, right? But if you don't know where to plug in those numbers, that's when you're gonna it's gonna be very difficult to solve these equations. So let's try a practice problem. We have a cup of water going from 33 degrees Celsius to 79 degrees Celsius. Is this an endo or an exothermic reaction, or endothermic or exothermic process?
Let's see here. So we're going from a cold temperature to a warmer temperature, so it should be an endothermic process.
Yes. So this can be a little bit difficult to think about. So what I like to do is draw this one stair step me. If you guys have taken physics 2A, this should be really easy for you. If you haven't taken physics 2A, and you know this, you're going to be in really good shape going into physics 2A, because this is one of the first things we talk about. So here's our lowest phase of matter. This is a solid.
Solid.
Whoops. This is a liquid.
Liquid.
And then this is a gas.
That's the gas.
So if we have water at, and this is our boiling point, and this is our melting point. So if we have water at 33 degrees Celsius and it's going to 79 degrees Celsius, it's going to be somewhere here on the liquid slope, and it's going to increase upwards into a higher temperature, but it's still liquid. And if you remember, on our x-axis, it's energy added or removed. So if you travel this way on the x-axis, your energy is increasing. So therefore, we're adding energy to the system. making this an endothermic process. Okay, condensing steam to liquid water at 100 degrees Celsius.
Well,
so we have steam maybe here. Wait, is that right?
It should be like on the other side.
My axes are off. Hold up, I gotta make this taller. That's boiling point. No.
No, it's fine. It's fine. No, you just like put the steam on this side because this is like gas and liquid equilibrium.
Yeah, got it. Yeah. So our steam is here, and we're going backwards to liquid water. So where liquid want to go?
Right here. It would actually wait. I take it back. It would be right here. The dot would be right here.
Yeah. So okay.
Sorry.
We're going backwards to make this liquid. So when we move backwards, we're removing energy to make it a lower state of energy. So this is going to be XO. So another way to think about it, if the three-step diagram thing is kind of confusing for you, is if you think about steam, steam is a gas, right? And if you know gases, they're very excited. They move around a lot. We learned from the what's it called, that one molecular theory of gases, kinetic energy something, that gas particles, they move around very, very quickly, very, very randomly. So if you know how gas molecules behave versus how liquid molecules behave, how do liquid molecules behave? They're like very...
like flowing.
They're kind of like just chill, flowing around.
It's like, hey.
Yeah, so to get from a gas to a liquid, what are you going to have to do to get those molecules from excited to not excited?
Cool them down.
Exactly. You're going to have to remove energy. And by removing energy, you're going to make them move slowly. When they move slowly, they're going to behave more like a liquid. So that's why it's going to be exothermic, because you have to release energy or remove energy from the system to get those molecules to a calmer state of matter.
Pure Zen.
Okay, and then next, dry ice sublimates to gaseous H2O. For this, it's a really good idea to memorize the SLG thingy.
Yeah.
So when we're going from a solid to a liquid to a gas, we're heating things up. So this is going to be endo. And then the other side will be exo. So dry ice means that it's going to go from a solid straight into a gas. So this is going to be an endothermic process. Is that right?
Yeah, no, that's right. Because you're putting in energy to make the you're putting in energy to going from a very stable state, like solid, to a more like random state, which is gas.
Oh, right, okay. Yeah, so it's kind of weird, but just stick with this and you'll be fine for the exam.
Yeah, and I threw y'all a bone for that one, for whatever. I'm
alrighty, and then next, which is the best at storing energy and maintaining a small temperature change? So for this, we gave you specifics.
Yeah.
So I remember Dr. E was like, pick the lowest or the highest one. That's your best bet of getting it correct. So we can cross out ethanol, because according to Dr. E, pick either the lowest or the highest value for these types of questions. So we can delete ethanol. So now we have to choose between water or iron. So let's look at the question. Which is the best at storing energy, maintaining a small temperature change?
So does that mean that like, so the one that has the most energy, but like with the smallest amount of temperature? So
yeah.
Oh, okay.
Yeah, so if you look at water requires 4.2 joules per degrees Celsius, or 4.2 joules to raise 1 gram of water by 1 degree Celsius. But iron requires 0.45 joules to raise 1 gram of iron 1 degrees by 1 degree Celsius.
So iron.
So you're going to have to add a bunch of water or a bunch of energy to change the temperature of water by like 1 degree. So if we added the same amount for iron, it would be like super, super high.
Yeah.
And we want a small temperature change. So therefore, the answer is going to be water.
Oh, yeah, that's right. Water.
Yeah.
Yeah.
So I don't know, a good example that helped me like think about water is that sometimes, have you seen like those doggy beds that they sell for like your dog in the summer? But instead of like a regular bed, it's like a water bed. There's like water inside it. And it's like really good apparently because water, because of those hydrogen bonds, it's going to be like very difficult to change or raise the temperature. So we're going to need to add a lot of water. Or have you seen that one science experiment where it's like a water balloon and then you hold it over like a candle versus like an empty balloon? It's because water is so good at like absorbing energy that there's going to be a very small temperature change.
Yeah. And
it's because of water's very high specific heat.
Oh yeah, we can look at the other stuff. But yeah.
Alrighty, so what time is it?
We're kind of yeah, you know, we got like 20 minutes left, so we're gonna go for overtime.
Okay,
we're gonna bore you all.
I'm gonna skip this part because this should be in your notes.
Pass.
Hopefully
yeah.
You have good notes. And,
just pass. INF.
Okay, let's try a practice problem. You have an insulated container with 1 liter of liquid water at 100 degrees Celsius. A piece of iron weighing 404 grams is dropped in the insulated beaker. And the final temperature of the water and iron is 28 degrees Celsius. What was the original temperature of the iron? So for this, I always like to draw a picture really quickly. We have a container.
Yeah.
It's full of water. And the water is at 100 degrees Celsius. And then we put in a chunk of iron. So it's in there. And then this causes the water to go down to 28 degrees Celsius. And we want to know what was the original temperature of the iron. So let's
do some
math.
Quick maths.
Okay, specific heat of iron is that, okay. So basically, because the beaker was, or because the container was an insulated container, you can assume that this is a closed system. So when the iron was dropped in, it made the temperature of the water go down. So we can assume that the original temperature of the iron has to be very, very cold, right? Because the water was originally 100. We dropped in a very cold piece of iron that made the water's temperature go down. So this is a good way to like kind of think about what you have to do to be on the right track for these equations. And then, so now let's draw our three-phase diagram. This is going to be 100 degrees Celsius, 0 degrees Celsius for water, because this is the boiling point. This is the melting point. Okay, so first, let's calculate how much energy it took or how much energy did water lose when the iron was dropped in to decrease its temperature. So initially, the water was at 100 degrees Celsius, right here, and then it changed down to 28 degrees Celsius, thanks.
Mm-hmm.
Okay, and then that was it, right?
Yeah.
There was no phase change. There was only one temperature change. So let's do our T change formula. It's going to be joules is equal to grams of water. I think it was 1 liter of water, right?
Is it 1 liter?
Yeah, it was 1 liter of water, but we know that water's density means 1,000 grams per ml. So it means we have 1,000 grams of water times specific heat of water, which is 4.184 joules per gram degrees Celsius, times temperature change of water. So it's always going to be final minus initial, so TFTI. Thanks for the invite. It's going to be 28 minus 100 degrees C. Okay, so joules is going to be equal to, let's punch in our calculator, 1,000 times 4.184 times 28 minus 100. And we should get negative 30,000, or actually 301,000 248 joules. Okay, so let's check our units. We have joules, that's correct. And we have a negative sign. So let's think about that. Does that make sense for joules to be negative in this case?
Yeah, it does make sense. Since you're going from a high temperature to a low temperature, energy should be being released.
Exactly. Okay, so we calculated how much energy water lost when the iron was added in, right? So now let's focus on the iron, because the question was, what was the original temperature of the iron? So the iron, let's draw a separate one for the iron.
Iron.
I'm just going to draw two, because iron, it stayed solid the whole time. So iron was initially very, very cold, right?
Yeah.
So down here. But iron, it got warmer because it absorbed some of the energy given off by the very hot water. So we can assume that the iron's temperature went up. We just don't know to what temperature, right? So now let's do a T change for the iron. So we have, I think, how many grams of iron? It was 401 grams of iron.
Yeah.
Times specific heat of iron, which is
4.451.
Times temperature change of iron. So TF, which is 28 degrees, right?
Yeah.
Minus TI, which was the
404 grams.
Oh, whoops, thanks.
Thank you.
Thanks. All right, so solving equation, we cannot have two unknowns, right?
Yeah.
Our unknown for sure is TI, which is temperature initial of the iron. So we're missing joules. We need to know joules in order to be able to solve this equation. So where do we get that number from?
Get it from the previous one.
It's going to be from the water, right? Because this is an insulated beaker, the energy lost by the water was all gained by the iron. Because this is the closed system, those two substances can only exchange energy with each other. So we can assume that this amount of energy was the amount that iron gained when it got dropped into the hot water and heated up. So now let's solve this equation. Math.
Wait, do we change the sign? Because since the iron is now our system, it's the one that's gaining the energy. So it changes the sign. That's the reason why that it went from a negative. So that's when your Q or your J or your capital J or your joules goes from a negative 300,000 to a positive 300,000. And also you don't need to know about the temperature thing for the iron. It's irrelevant. It's just an example. Yeah.
Yes. So energy lost by the water was gained by the iron. That's why it's going to be a positive sign. This is like the iron is like endothermic now because it was gaining some energy when it heated up. So math times 0.451, you get 182 times 28 minus TI. Distributive property times 28.
Like algebra, we do this. But I'm just gonna. Anyway, I got time for algebra.
Okay, well, this is like how I solve it. Okay, so now we're gonna do minus 301, 248, and we should get 296,146 equal to negative 182 times TI. TI of the iron is going to be divided by 182. Going to be negative 162.7 degrees Celsius.
That's some cold-blooded iron.
All right, so now let's think about this. Does this answer make sense?
Well, the iron should be like super, super cold. So yeah, it should be a negative value.
Right, because if you think about it, the water was at 100 degrees Celsius. Now it's like boiling water, right? Very, very hot. If you touch it, you're going to burn. But when the iron was dropped in, it dropped all the way down to 28 degrees Celsius. That means the iron must have been very, very cold in order to make such a giant temperature change like
that? So heat of formation. So the definition of heat of formation, it's the amount of energy required to make 1 mole of a molecule. And the units are typically in kilojoules per mole. So on the left right here, those are just like examples of like what the standard enthalpies or standard heat of formations for several different compounds at a certain given temperature. Do note that changing the temperature does change the amount of energy. So, and then does change the amount of energy. So if you're going to change from, from like carbon into diamond, it requires a very, very amount of like high temperature and pressure. But that's something you all don't need to know about. Just know the definition that it's that heat of formation is the amount of energy required to make 1 mole of a molecule. All right, so slide. So most of the molecules are formed by releasing or absorbing energy. However, pure molecules, aka the molecules that naturally exist in nature, will have 0 enthalpies. So meaning that like pure substance molecules will not need to make energy because we will not need to release or absorb energy because they already exist like that in nature. So the diatomic gases right there, so H2, N2, F2, O2, I2, Cl2, and Br2. So all those diatomic gases do not require any energy to be made or released. And then solids such as like sodium, potassium, iron, and calcium, they don't need energy because that's how they exist in nature. And so does carbon. Carbon exists in nature, but I believe it's carbon graphites. So be sure to note which carbon that is. I believe Dr. E went over something like that in class where it's carbon graphite, not just carbon by itself, which is the reason why that it takes so much energy and pressure to make from carbon graphite into diamonds. So yeah, slide. Oh, so the heat of reaction. So it's the heat of reaction is the amount of energy needed to be released or absorbed used for a chemical reaction. So the enthalpy of the reaction or the heat of the reaction is equal to the sum of the products minus the sum of the reactants. That's all you need to know for that one. Products minus reactants. Do note that, I think I'll show you in the next slide. Do note that if your reaction has more, if your reaction has more than 1 moles, you have to incorporate that into your calculations. Whoops. How am I going forward? That's not supposed to be shown. It's supposed to be a surprise. We'll just use yours. All right, so calculate the enthalpy change for the combustion reaction of glucose. So sugar and it's gone. Where are we going? Where my car go? Okay, so of glucose to carbon dioxide and water. So here's your reaction, and then the heat of formations are the one below. So it takes negative 1,260 kilojoules per mole to make 1 mole of glucose, which is C6H12O6. It requires negative 393.5 kilojoules per mole to make CO2, and it requires negative 285.8 kilojoules per mole to make 1 mole of water. Now then, why do we not have the oxygen in there? Oh, whoops. So the reason why we don't have the oxygen in here as a list is because oxygen does not need any enthalpy to be made. It already,
how it naturally exists.
Yeah, it naturally exists as a diatomic gas. So a test question would be, what would be the enthalpy of, I don't know, of hydrogen gas? You would pick 0 because that's how it naturally exists in nature. So yeah, why don't we do this problem? Annotate. All right, so C6, give me the freaking H12O6 plus 6O2 produces what is it, 6CO2?
No.
It was 6CO2?
Wait, is this cellular respiration? Maybe.
Maybe? How do you know? I think it was 6H2O. I'm assuming this is it. I can't do math. All right, so that's 12. That's 12, 18, 12, 18. This is 6. This is 12. That's 12. Yeah, this is it. All right, so you would have to use your products minus reactions for equation. So the enthalpy, delta H, back. Back. Where's my mouse? Where'd my car go? H of reaction. Looks so. How come I can't clear it? This is so awkward. Wait. Are you reviewing my work? Can you press clear? Or you can't? This is some bullshit. This thing? This is so awkward. Whatever. All right. Delta H reaction is equal to N sigma delta H formation of products. There's an F there. Product minus N sigma delta H formation of reactants. So products minus reactants. That's all you need to know about it. So can I not even change this gosh dang color? So delta H of reaction. Now I'm getting annoyed. Are you freaking? It's not fucking. I got myself. Okay. Can I not touch this thing? This is some bullshit. Bullshit. Can you actually not really touch this effing thing? This is like. Oh my god. No. Michael's struggle bus. You're struggling. I'm choking really hard right now. I'm really choking really hard. Punishment. Damn, they got me the first half, not gonna lie. This is the reason why I gotta come on to these things. This is some horseman off. Can I not really touch? Oh, I can touch something. I can touch it. I can finally touch it. Claire, finally, gosh dang it. Yeah. Just give me that fucking thing. Okay, let's try this one more gosh dang time. All right, so, well, this feels much more clear. Why did we do this in the first fucking place? I'm so pissed. H2O6 plus 6O2 produces 6H2O plus 6CO2. Oh my gosh, this feels so amazing. It feels so liberated. It feels invigorating. So delta H, a formation of C6H12O6 was, what was it, negative 1270? Negative 1270? I think it was negative 1270. Can someone check that for me, please? Negative 1270. Negative 1270. Can someone check that for me? I don't remember my own equation or question. 1260, thank you. 60 kilojoules per mole. Delta H, a formation of H2O liquid or gas, was gas. 393.5 kilo. No, that was the other one. This is CO2. This is CO2. CO2 was 285, right? 285. Negative 285? Negative 285. Oh, fuck. That is negative. 280. Of course. Is that a liquid? It is liquid. That actually changes everything. 25. CO2 gas is negative 383, 393. 93. I can do this, coach. 93.5 kilojoules. So we're going to do the products minus reactants for all of this. So let's just make some espace right here. So the delta H. Use a different color. Delta H, delta H of reaction is equal to the products, which is H2O and CO2. So it's 6 times negative 285.8 plus 6 times negative 393.5. So this is 1 minus the C6H12O6, which is negative 1260. And this is in kilojoules per mole. That means your final answer should be whatever the quick maths is this. So the delta H reaction of this should be in, I can't do math right now. What's up? The value? Was that it? Oh, all right. I'm trusting y'all on this one. Negative 2815.8 kilojoules per mole. I'm trusting y'all on this one. All right. So this is the delta H reaction for this problem. So delta H is always products minus reactants. All right. So clear this off, and we're gonna go to the next one. Hess's law. So, question: does anyone know how long it takes for a typical chemical reaction to completely react?
Minutes.
2 minutes. Well, it depends on the reaction, and chemists ain't got no time for that. So ain't nobody got time for that. So we got our boy Hess over here. So what Hess's law is supposed to mean is that chemists have lives of their own, right? They have lives. They have their lives, so they don't have X amount of time to go and to do a reaction. So what Hess found out was that you can actually find the amount of energy required to like have a reaction just by using smaller reactions. So basically, Hess's law is used to calculate the chemical reaction by using smaller reactions. So you're basically using the clones of the reaction to be very proud of your overall big reaction, which is the reason why that little diagram over here, to go from A to D, you have to go to A to B, then B to C, then C to D to get the overall A to D. So it's taking like little steps. So you use the smaller reactions and then you add them all together to get the amount of energy required for your desired reaction. Basically, you're using your little clones and you'll be very impressed of it, and then you'll also be very proud. So here's the Hess's law reaction. So calculate the heat of reaction for the combustion of methane. So methane right here is the one in red. But we know that it takes about like X amount of years in order to, well, X amount of time to actually have the reaction. So in order to find it, we will use these 3 smaller reactions and then make these 3 look like the methane reaction, which is the one in red. So now then, let's try to work on this thing one more gosh dang time. Mind in control, mind the coach. Let's try this one more gosh dang. Try this one more time. I'm going to be very upset. Back. So then so one of them was C plus F. I forgot my own reactions. Thank you. C plus 2H2, CH4. This is 74.8 kilojoules. Change this one. This one is C plus O2 produces CO2, negative 393.5 kilojoules. The other one is, y'all can still hear us, right? H2 plus 1/2 O2. We haven't bored y'all yet, right? 1/2 O2, H2O. All right. So, and negative 285.8 kilojoules. So how I look at it, I always look at it as a puzzle. So what I want to do is get my 3 reactions to have the same, to be on the same side as the big one in orange, even though that one of them is in also orange, but it's fine. So I always work from left to right. So the first one is methane. Out of my 3 reactions, which one is the one that has the methane?
First one.
The first one. So the first one has the methane, but is it on the right side?
No.
No, it's not on the right side. It's on the opposite side. So what I do is I flip this reaction. So this one we flip, stop flipping, flip. This one will be flip, and you also will flip the sign. This will also be flip. So you'll flip. So if you flip the reaction, you will flip the sign of the amount of energy. So that's the first one. Now then, O2. Which one of these reactions has O2?
Second.
And?
Third one.
And the third one. So 2 of these reactions have O2. So let's not focus on O2. Let's try CO2. Which one of these reactions has CO2 on it? The second one. So the second one has CO2. Is it on the right side?
Yes.
Yeah. So CO2 is on the right side, so we don't have to worry about it. Now then, what about H2O? Where is it? Which one of the reactions?
Last one.
The third one has the H2O, but is it on the right side?
8.
Is it the same amount of moles?
No.
No, it doesn't have the same amount of moles. So what we had to do is we had to change this reaction
Yellow.
to have this, right, this is a Shaniqua looking ass color. Shaniqua looking color, sorry. We will have to change this in order to have the same amount of moles as the reaction, but whatever we do to that, we also change the delta H of this. So, fine, we'll just be fine. Let's see here, where'd my card go? All right, so we're gonna clear all of this. So we're gonna clear all of it. So now, the reaction that we want is CH4 plus 2O2 produce to CO2 plus H2O. Now then, the first one we flipped, which is now, we'll put this back in orange. So CH4 produces C plus 2H2. This one is now negative 74.8 kilojoules. The second one, we left it the same. So C plus O2 produces CO2. And this has negative 393.5 kilojoules. We were over time. And the third one, we multiplied by 2. So this one's actually 2H2 plus 1O2 produces 2H2O, and this is times 2. So this is actually negative 6, carry the 1.1, carry the 1, 29, 28, 570. Thank you, 571. Thank you. I actually had a panic moment right there. So that one is negative 571 kilojoules. All right, so then, now all we have to do is cancel out like terms. So whatever's on the left and it's on the right, they'll cancel out with each other. So from these reactions, we know that carbon and carbon will cancel each other out once we add them all together. And then we will also cancel out 2H2 and 2H2. So we'll cancel out both of those. So now, once we combine all 4 of these, all 4 of them should look like CH4. So once we combine, once we add all 4 of these, you should have CH4 plus, this is purple, 2O2 produces, what the hell is the red one? CO2 plus 2H2O. Now then, after combining all of that, now we add all in our energies to the right side. So we know the overall energy is, the delta H of this is, I can't do math. Negative 1,030, actually negative 1,040 kilojoules. So this is the amount of heat required to make this reaction, well, go. So it's 1,000 F words. 1040 kilojoules. Right?
Is this endothermic or exothermic?
Oh, this reaction would be exothermic because since the sign is negative, that means we're releasing energy. If the sign is positive, then it's an endothermic process. So now then, so that is pretty much it that we have. Thank you again for everyone to logging on to this and seeing that whole escapades of us. But yeah, if you have, yeah, so good luck with studying with the test. We can leave open the chat box for y'all if you want to like discuss anything. Also, for the attendance, make sure all of you sign up for the attendance sheet and like put in your student ID and like your name in it because we need that information, that data. So please make sure that you fill out the attendance sheet. Don't just get the link and then just like, oh yeah, and then they're not gonna like worry about us. But yeah, make sure you fill out the attendance sheet and also do the survey for our virtual SI. The survey should be on the homepage of each of your respective sections. It's like in bright red all the way on top of the homepage. Make sure to fill out that. Next following week is our last week for actual in-person SI sessions. So be sure to attend those if you can. So yeah, thank you again. We'll leave this on here for like to answer you all's any questions about it. But yeah, if y'all don't have any other questions, then thank you for logging on, and we'll see you all on Monday. Good luck, everybody.